Greetings. I'm Joe French, coming to you from my classroom in Mount Pleasant, Utah. And this is topic 2.2 of the AP Calculus curriculum, defining the derivative of a function and using derivative notation. So during this video, that's exactly what we're going to do. We're going to define the derivative as the instantaneous rate of change of a function. We're also going to recognize various derivative notations. How do we talk about a derivative without using a lot of cumbersome language? Okay, so the derivative, in the last section, the last topic, 2.1, we talked about the instantaneous rate of change, which was the limit of the ratio of the change in output over the change in input, as the change in input approaches 0. So when we looked at that, we looked at what happens when we change our input and output and bring them closer and closer together. What's going to happen to that ratio? When we bring them absolutely on top of each other, it becomes undefined, but we can hopefully see a trend or an expectation, a limit to those values of that ratio as those 2 points come together. So our change in y over our change in x as our change in x disappears. We could also write that as the change in two y values over the change in two x values, x1 and x2, f of x1 and f of x2. Another way to think about it is our first point could be x1, and then our second point, x2, could be our first point plus a small value. So if my first point was x or 1, then maybe my second point is going to be 1 plus 0.01. Then when we recreate our change in y over change in x, we would have our 2 points, x and f of x, and x plus h, and f of x plus h. So our difference quotient now looks like our second y value, f of x plus h, minus our first y value, f of x, over our change in x's, x plus h minus x, which just leaves us with h. And then we're interested in what happens when that difference goes away. An alternative form is, let's say we're interested in what's happening at a specific point, a comma f of a. So we have a value there. Then we want to know what happens when we bring this variable point, x, closer and closer to the point we're actually interested in, a comma f of a. In that case, we then look at our difference quotient here as f of x minus f of a over x minus a, and we're interested in what happens as x gets closer to a. Now all of these difference quotients are calculations of a slope, a change in y over change in x, and the limit is the slope of the tangent line. When these 2 points aren't the same, we get a secant line, but when they are the same, when we've converged on a single point, then we get the slope of a tangent line to the curve at x equals a, and it's denoted as f prime. This f prime is our notation for the derivative. We have another notation. This f prime can also be denoted as this d over dx of f of x. These mean exactly the same thing. They're both notations for the derivative. They just come from different places. Two gentlemen in the past basically came up with the ideas for calculus right around the same time, and they used different notation to explain their ideas, and neither notation became a dominant notation. They both became equally important in describing the ideas of calculus. So this f prime, as we would say, is equally as important as the d dx of f of x. These notations refer to the derivative. And the derivative itself is the slope of the tangent line on a curve, and it's also the instantaneous rate of change of the curve at a point. In specific instances, when we're talking about position and how your position is changing, then this derivative can be your instantaneous velocity. So to wrap it up, our derivative is the instantaneous rate of change of a function, also known as the slope of the tangent line, or in some cases, velocity. The notation we use is f prime of x, or d dx of f of x. We'll be working on some examples soon.